All right, we are in week number 10. And we did, in my opinion, the heavy lifting on Monday. All right, week number 10 has three sections in it. They are 15.5, 15.6, and then 15.8. We got through 15.5 and 15.6 last time because I just wanted to, like I said, just go ahead and get the worst of it done. I did tell you that if you had any questions about either one of those, that we can revisit them as needed today. So, with that in mind, is there anything from 15.5, which was the rationalization of denominators? And is there anything from 15.6, which was the solving of radical equations, that we need to revisit? Is there a problem, a homework exercise that you had trouble with, or is everyone making good progress? Caden, Ethan, anybody here have oh, we got folks joining late. Anybody, anybody need anything? Everybody doing well? Everybody okay? If I hear nothing, I'm going to assume that you don't have any specific questions, specific problem numbers that we need to look at. What do you think? Doing all right. Okay, thank you, Katie. That sounds good. All righty. I'll give it another second or two, and then we'll jump into the next item on the agenda. Okay, not hearing anything. Again, I hope you all are in fact doing well. The next thing we need to look at is something called the complex number system. We're going to do a brief introduction with something called the complex numbers. So let's just go ahead and go there. All right, Sweeney. I have a feeling I'm gonna be checking a lot of names off after the fact. All right, so complex numbers. Let me give you shall we say, a little bit of history on this. All right, here's basically, at least my interpretation of the history. Here's basically what happened. There a point in time came when there were equations that needed to be solved, and we couldn't solve them. All right. And it wasn't because, not necessarily in every case, because they were horribly complicated equations. We had been solving equations just like them for some time, but again, we ran into a roadblock. Well, let me first give you an example of an equation that we were able to solve, and then compare that to an equation that we were not able to solve. So let's say we had x squared equals 4. Let's keep it simple. We don't need to get overly complicated here. Let's stick to the basics. There are a number of ways to solve an equation like that. You could be as elaborate as using the quadratic formula, but it is certainly unnecessary. You could set it equal to 0 and factor, but that's definitely unnecessary. The easy way to solve this one is to extract roots, meaning I would just take square root of both sides. And let's just say, for the sake of argument, I'm only looking for the positive answer. Again, keeping it straightforward, keeping it simple. When you take the square root of both sides, you get x equals 2. That's the positive answer. And as I've stated, that's the only one I really want to think about right now at this moment. There it is. Extraction of roots says take the square root of both sides. All right. So you can see that equation was not complicated. Let's do it again. Let's say something may go easier. X squared equals 1. How would you solve it? Take the square root of both sides, and you get x equal 1. Very easy, very straightforward, very, very, very simple. All right. But let me drop down the page here. Let's say we had something like x squared equals -1. Let's look at a problem like that. Well, when I take the square root of both sides, I get x equal And here's where the problem came way back then. The problem was we couldn't take the square root of negative numbers. And I'd be willing to bet that at some point in time, somewhere in a math class, some time in your past, you've been told that you can't take the square root of a negative number. Anybody remember? Everybody ever been told that? Can't take the square root of a negative number?
I believe I have been told that,
Yes. Well, that, John, is not entirely the truth. That's not the whole truth. All right.
which is
And
crazy.
do what?
Which is crazy, being that this is something I was taught in public school by a teacher.
Well,
You
let me
know,
show
it's
you.
it's crazy the
That,
things that
that they were
change.
trying to keep it straightforward and not confuse folks. So let's do this.
Right.
Let me just sort
Okay.
of show you the motivation for them saying that. Let me just get a clean piece of paper here. There are a lot of different, shall we say, groups of numbers, and they have names. For example, if you look at numbers like 1, 2, 3, 4, 5, 6, and so on, the dot, dot, dot means they go on forever. These are sometimes called the counting numbers. If you were sitting there counting things, these are called counting numbers on occasion because these are the numbers you would use. If you're counting the fingers on your hands and the toes on your feet, these are the numbers that you would use. Technically, they're natural numbers. All right. So at one point in time, humanity, shall we say, these are the numbers they had. They knew how to count. But you can't solve every problem with one of these numbers. All right. So what they did was they said, well, okay, there's more that is needed. We will throw the number 0, a number that represents none, in, and we get something called the whole numbers. And I'm drawing these in boxes, little concentric boxes like this, as to say that the whole numbers include 0 with all of those thrown in additionally. All right, so the natural numbers contain only these. The whole numbers contain 0 and those. And again, 0 is a very important number. I don't know if you've ever given that a whole lot of thought, but it is phenomenally important. So when we developed the whole numbers, that was a big step forward. A number that means none is really important. We, for example, would not have a place value without it, is just, for example. All right. And then we said, okay, this is good. This is better. We can solve a lot of problems with this, but this is not enough. This is not everything. We then took the natural numbers and came up with their opposites. And we said, okay, we can solve a lot more problems with that than what we could before. That's great. Those are your integers. All right. So again, the integers contain these negative numbers. Integers include 0. Integers include your natural numbers. All right. Then we said, yes, we can solve a whole lot of problems with all of this. We can do a lot of math with all of this, but we can't do everything. We need more. All right. The next thing we did is we threw in all of the numbers, any number that can be written in fractional form. They often symbolize this with an A over B. So these are your decimals, like, like 0.5. These are your fractions like 3/4. Okay. So all your decimals, all your fractions, or anything that could be written as a fraction. So for example, 1/3, which is that repeating 3, can be written as a fraction. So it's in here as well, which means all of these numbers can also be written as a fraction. You can take a 4 and write it as a 4 over 1. You can take -3 and write it as -3 over 1. And you've got a fraction where both top and bottom, both numerator and denominator, are integers. So there we go. All right, these are called rational. All right, so there's been forever a process of, okay, there are math problems we can't solve, so let's add to what we know about the numbers that exist. Now, I said rational means can be written as a fraction. What about those numbers that can't be written as a fraction? Well, that's where there's a little bit of a break here. We say, okay, irrational. Right? Irrational means you cannot write it in fractional form. Those are things like your square root of 2, your square root of 3. Square root of 4 is not here because square root of 4 is 2 and it's over here. Square root of 5 is here, etc. Okay. You've seen things like pi from geometry class. Pi is that 3.14, that decimal that goes on forever with no discernible pattern to it. Those numbers that have repeating patterns, again, they can be written as a fraction, like you're repeating threes and you're 125, 125, 125. Those are over here. Irrational are over there. Okay. What happened next was, okay, we would like to be able to solve problems using all of these. So let's create a group that includes them all, and those are your real numbers. And I know that the material didn't call for it, but I wanted you to have a quick review of all these different, real quick. I didn't take up your whole day, but just a real quick review of all these different number systems. All of these together make up the real numbers. And the thing is, John, that when you're in the public schools, high school, middle school, elementary school, whatever, you spend majority, I will say like 99.9% of your time doing math. And I don't mean just in math class. I'm talking about physics if you decided to take it in high school, chemistry, which I think everybody has to take, your biology, which everybody has to take some. Those all use the real numbers. Okay. The real numbers will solve any problem in any of the elementary school, middle school, high school level classes. And that's why they say, that's why you were told you can't take the square root of a negative number. And the reason they said that was because when you're in the real numbers, you can't. All right. Square root of 2 is here. Square root of 3 is here. Square root of 4 is right over here. Square root of 5 is here. But the square root of -1, it's not in any of this. All right. The square roots
Right.
of these negative numbers, they aren't real numbers. So, John,
That
don't you
makes
think that's
sense.
just a little bit of a justification for why they told you that?
Yes. Yeah. Yeah. Yeah.
Yeah. They're basically what they were telling you is
That
you
would
can't
have went over my head at that point. You
that.
know,
Well, I don't want to say that and be rude, but yeah, it basically
I
would.
mean, I mean, for sure it would
When
have.
you're an
And
elementary school
when I was
kid,
in elementary school, yeah.
yeah, this would go over your head. So here's what happened. They got to problems like this. They got
Right.
to answers that looked like this, and they said, that's not in here anywhere. That is not here. So what we needed to do, what had to be done was a new number had to be invented. Again, one that's not in here anywhere. So we invented what's called the imaginary unit. We symbolize it with a lowercase I, and I is defined as the square root of -1. And I know it's when you've spent so much of your life working with nothing but these real numbers, all of a sudden you get a number like this and it just feels unnatural. But again, it had to happen because there were problems that couldn't be solved. All right. So outside the real numbers, all of a sudden we have this brand new set of numbers called the imaginaries. And the very first one you are typically introduced to is I. And others would be things like, 3i and -1/2 I. And in other words, take any real number and put an I next to it. And that identifies it as being an imaginary number. So your identifier for your imaginary numbers is that I. And of course, you do not want to restrict yourself to using just real numbers for some problems or just imaginary numbers for other problems. You want to be able to use both. All right. So if you take all of these, all of the reals and all the imaginaries, and you throw them in together, what you end up with is the complex numbers. Okay. So what might a complex number look like? Well, just some examples. A complex number will have a real part to it. It will have an imaginary part to it. Technically, all of your reals are also complex. They're just, these numbers over here are complex numbers with a 0 for the imaginary portion. These are all complex with just a 0 for the real portion. But things with a bit of both would be things like 3 plus 5i. That's a complex number. Here's the real portion. There's the imaginary portion. The I is what says. Here it is. This is the imaginary part. All right. So a 1/2 minus 3/8 I would be a complex number. Again, here's your real part, and here's your imaginary part. The negative 3/8 is the imaginary part because it's got the I sitting there saying, hey, here I am. I'm the imaginary portion of this complex number. All right. So some of the first problems that you will run into is they will throw a complex number at you like -7/5 plus square root of 5i. And they will say, well, of this, which part is real? The real part is the -7/5. And of this, which part is imaginary? Well, the imaginary is square root of 5. Don't put, oops, sorry, that went off the screen. Don't put the I in there because, again, the I is there to tell you here is the imaginary part. So you'll have a few questions like that. They should be, frankly, just real trivial for you. You have like an 8 plus 5i, and they'll say, what's the real part? Well, the real part's the 8. What's the imaginary part? It's just the 5. The I says so. The fact that the I is sitting there tells me so. Now, some of the properties that they obey. Here are some things that are true. For a complex number to equal another complex number, the real part has to equal the real, and the imaginary part has to equal the imaginary. All right. So again, they might say 15x plus square root of 13i equal to 30 plus 10yi. And they will say solve for x and y. Well, again, for these numbers to be equal, the real part has to equal the real, and the imaginary has to equal the imaginary. So what that says is, since real parts are here, that means 15x must equal 30. I'm dividing both sides by 15. That means x is 2. And imaginary part has to equal imaginary part. So square root of 13 must equal 10y. I'm dividing by 10. What that says is the y equals square root of 13 over 10. And you'll see a handful of these. These, again, should be just trivial. All right. They will also have some simplification problems. All right. Remember, when you take the square root of a positive number, like when you take the square root of 4, you just get 2. But if you take the square root of -4, the fact there's a negative underneath the square root means you've just stepped over into the imaginary numbers. So square root of 4 is 2, but square root of -4 would be 2i. The negative on there says you have to introduce the I. So if you have square root of -32, you would break that down as the square root of -1. And if you recall, I told you that it would be helpful for you to have just in your head, a list of perfect squares. You know, like 4 is a perfect square because the square root of 4 is 2. 9 is a perfect square because the square root of 9 is 3. Well, you've got a brand new perfect square to memorize. -1 is now considered a perfect square because the square root of -1 is I. So for the -32, you got a -1, and you've got a 16 and a 2. Square root of -1 is the I. Square root of 16 is 4. and 2 is something we still can't take the square root of, and that's not going to change. All right, that will not change. So let me just sort of page through here. If you had the square root of negative 81, that'd be a 9i, because the square root of 81 is 9, and the negative makes it an I. And everybody with me so far? It's a really simple section. It's not going to take very
Yeah, I'm
long.
with you.
Do what now?
I said I'm with you, Mr. Geller.
All right. All right. Good, good, good. All right. They have some others here where we need to learn how to add and subtract. And you're like, wait a minute. I know how to add and subtract. Well, they're brand new numbers. All right. So adding and subtracting is something we have to look at. Don't worry. It is certainly not complicated. There are formulas that you'll see in a lot of books, which honestly make it look complicated, but that's just not the case. If you had something like A plus BI, here's what the formulas will tell you. A plus BI plus C plus DI, and you're like, good grief, that's a whole lot of letters. This just comes out to be A plus C. Oh, put the A first. Keep it in order. A plus C plus B plus D I. And again, a lot of people would look at that and say, oh, good grief, that is a formula. Am I going to have to memorize that? Well, no, not really. Okay, no, not really. If you had something like 3 minus 7i, and you wanted to add to that negative 2 plus 11i, if you were a person who was just seeing algebra for the first time, I know that's not you. You guys have seen it before. I get it. But just try and pretend. Just try and imagine. If you're seeing algebra for the first time, you might look at this and think, well, that I, that's just a variable. That's just like an X or something. And therefore, what I need to do here is this thing we've been learning calling, what's it called? Oh, combining like terms. Well, if you were to look at it like that, it would still work. You would say, well, 3 and negative 2 is a 1. Negative 7 and 11 is a 4. And you just put the I with it. And folks, that works. All right. That is what this formula is basically saying. This formula is saying add the reals to the reals, add the imaginary to the imaginary, and put the I next to it. And it will work. And interestingly enough, your calculator, a lot of what we're doing, your calculator can do. Not all, but a lot. But you will notice that on this calculator, if you hit mode, you'll notice that there's a real option here. And if you've got a TI-84, let's say you bought it new, it came factory settings, and you've never changed it, your calculator probably is set to real mode. But if you set it over to the A plus BI setting, which again is going to be your complex number mode, also note that right above your decimal point, there's a little letter I. All right. So if I was to come back to this problem, I'm going to do a parenthesis, 3 minus 7. Second function hit the decimal and it pops that I up. Close the parentheses, plus. Open the other parentheses, negative 2. Make sure you use the negative button, which is here. We're not subtracting. This is a negative. Okay, make sure you use the negative. Negative 2 plus 11. Second function decimal brings up the I. And when you hit the parentheses, you close them and hit enter. It'll give you that 11 plus 4i. Now, I'm not trying to show you how to cheat, but I do believe that there is technology available. It doesn't hurt to know how to do it both ways. I am not saying use the technology and don't do it by hand. I'm not saying do it by hand and don't learn technology. I'm saying that both things are of great value. It is, as educated folks going out into professional careers in the future, I think you should know both. All right. So let me just put another problem up here. Let's say I had a negative 10 plus 3i, and I was going to subtract from that a 5 minus 6i. The one thing with this one, let me write that a little bit more neatly. With this one, what you need to remember is distribute that minus sign. So writing it out in another step, negative 10 plus 3i, minus 5, minus a minus, make a plus 6i. Negative 10 and negative 5 is negative 15. 3 and 6 is 9. All right, so doing it by hand, that's the way it would look on the calculator. Parentheses, negative 10 plus 3, second function decimal brings up the I. Don't forget to close the parentheses. Minus, open the other parentheses. 5 minus 6, bring up the I, close all those parentheses, and you get the same result. All right, so the calculator will do the addition for you. It'll do the subtraction for you. Again, there are things it won't do, at least it won't do them well. Okay. If you had a problem like, let's say there's another one here that says square root of 11 plus 5i minus a negative 1 plus 8i. Well, with that one, with it having that square root of 11 in there, that's really not a good candidate for your calculator. And your calculator is not going to handle things like that all too well. So it'd be square root of 11 plus 5i minus minus and make a plus 1 minus 8i. Got to remember to distribute that minus sign. And square root of 11 plus 1 is just square root of 11 plus 1. There's no great way to do that. 5 minus 8 is minus 3i. So that, again, even though it does not come out looking really neat and clean, that one, that is right there, probably the best approach. Your calculator would turn that into some ugly decimal. And that's just not what Hawks is looking for. And it's good to know how to do that without the calculator turning it into a great big mess. If you had something like negative 7 minus 4i minus negative 3 plus 3i plus negative 3 plus 4i, that one, and I keep running off camera, I apologize. For that one, all the numbers are nice, clean numbers. They're nice, integers. Your calculator would fare very well with that problem. So first set of parentheses, negative 7 minus 4. Second function, hit the decimal, there's your I. Don't forget to close those parentheses, minus. Next set of parentheses, negative 3 plus 3. I, close those parentheses, plus negative 3 plus 4. Second function decimal is the I. Negative 7 minus 3i. Your calculator will do that one very well for you because of all of the very nice, clean integers. All right, there's another one that I want to do here, but I just skipped over it. This thing where they have you comparing real to real and imaginary to imaginary, I want to hit that again. Give me a second. Add. Okay. Come on now. Come on. Hawks is slow today. Have you all noticed that Hawks has days that just doesn't want to load up? It's really slow. Still waiting. Come on now. Okay, there.
Yeah, I do think that some days it's like it takes a little while when you click next, like to go to the next page, next problem,
Yeah, that's
where
exactly
it's
what I'm
like
running
just
into.
refreshing. Yeah.
All right. Here it is. Finally, I got it. I got it. I'm ready now. Here we are. Let's say I had 17x plus 17 over 5i equaling square root of 5 plus 10yi. All right. So again, the only way those numbers can be equal is if the real is equal to the real and the imaginary is equal to the imaginary. Here's the real. How do I know that's the real? Because there's no I attached. So 17x equals square root of 5. So divide both sides by 17. X is square root of 5 over 17. So there's the X solved for. Now, imaginary equal to imaginary. 17 fifths equals 10y. Again, how do I know those were the imaginary parts? Because I and I on both sides identify them as such. Multiplying by 1/10, or dividing by 10. I get y equals 17 over 50, because 10 times 5 would give me a 50 on the bottom. So there's my X and the Y. I wanted you to see one more of those. I thought that one looked a little bit different. So I wanted you to see it. Now, I will say that complex numbers system is a topic that I won't lie to you. The complex numbers can become quite ugly. They can. You're not going to see the ugly side of the complex numbers. It's just not going to happen. All right. You need, for your purposes, what you need is just an introduction to the basics, just getting started. And that's what this is. That's what Hawks is giving you right here, is just an introduction of getting started with the complex numbers. Nothing difficult, nothing crazy, nothing complicated, just everything that you need to know right now. All right. If you were to say, for example, hey, I feel like becoming an engineer, well, there will be more on that topic waiting for you in the future when it is the right time. But for now, that's it for the complex numbers. Short section. I hate to disappoint, but like I said on Monday, I really wanted to knock out the toughest, the worst, the lengthiest part of it on Monday. Leave something easy for Wednesday. So, what do you think? Everybody good with that?
Yeah, it makes sense to me, man. It makes
All
sense
right.
to me.
All
I
right.
think
Now,
good
what we
where
did
I'm at.
last time, I will say again, because I had a couple of folks join late. And I want to make sure everybody gets everything they need, takes away everything they need to take away. Last time, Monday, we did the rationalization of denominators and we solved radical equations. Is there any of that at all that we need to come back and take another look at? Anybody having any trouble, like to see another example, or do you feel like you're on the right, the right step in the right place, making good progress, however you want to say it? Everybody comfortable with this week's material?
Yeah, I'm doing good.
Yeah, I am in class.
All right, Caden's good. Alvarez, what do you think? Everybody's in good shape. Not everybody wants to talk to me. That's okay. I will take no insult. Everybody's good. All right, let me